This is Remy Pengel with the Center for Wind Energy at James Madison University. And today we're talking about the pre-host school research project, School Electricity Assessment Task 3B. This is the Alternative Energy Plan, Power Production Estimates, and Budget. So we will be first talking about understanding the wind and solar technology that's available to select. Then we'll talk about how to calculate power output from these technology. And then from there, we'll go over some suggested methodology, proposed tools, a proposed rubric, a proposed timeline, and ending with an explanation of some expert contacts that you may be able to utilize as you move forward with your project. So first of all, it's important to understand that wind turbine technology ranges in size, and with that ranges in application. So when we talk about size, we can talk about the physical size or the height or the blade length or swept area of a turbine, but we also talk about the rated capacity of the generator. So in this diagram, you see that we've got small turbines, what we call on-site turbines, that generate electricity at your home or your school for you yourself, as opposed to the utility scale turbines that are larger, generate a lot of electricity, are used in farms, and that electricity is sold to an electric provider who then sells the electricity to the customer. And again, they do range in size from generating up to 5 to 6 million watts to all the way down to 400 watts. And again, they range in application. And yes, there is variety in the market, not only in the size and generating capacity of the turbines, but also in the way they look. So a lot of times we are used to seeing the horizontal axis turbines with the 3 blades, but there are some different unique turbines out there. These vertical axis turbines here that look a little bit more like an egg beater or something are new onto the market. There are some other unique turbines that are made specifically for rooftops. So just things to keep in mind as you're looking for your technology. When it comes to solar technology, the market is not so variable. There are different sizes of solar panels in terms of their square footage and in terms of how much energy they produce, but not as much fluctuation as you might see with wind turbines. Here we're showing the different technology here, not so much the different sizes. And so there's a couple of different technologies in terms of photovoltaic cells. First, there's the monocrystalline, which means that it's one crystal of silicon or some other semiconductor. There's polycrystalline, which has many crystals inside of it. And then there's thin film, in which you don't actually even see the crystals. And there's pros and cons to each of them. There's an increase in efficiency between monocrystalline and polycrystalline. But there's probably a variation in cost as well. So there's a need to balance those things. And so the key here is to be sure that you're matching the technology to your needs. In this project, you've gone through and you understand now what your energy needs are, what your electricity needs are. And so you've been through the siting and the resource assessment, so you know what kind of resources are available to you in terms of wind and solar. So now it's important that you understand the technology that's available and how do you match that to your resource. So again, number 1, pick the technology that meets your electricity needs, which was task 2. Pick the technology that will work the best in your wind and or solar resource, which again was task 3A. And then now we're really focusing on picking the technology that fits your budget. So if your school needs, or your space that you've decided to look at for this project, uses 5,000 kilowatt hours every year, then you may not need a huge wind turbine or lots of solar panels. But if you picked a whole wing, maybe you're looking at more like, millions of kilowatt hours, and you may not have the budget or the wind resource or solar resource to really be able to put up that many solar panels or that large of a wind turbine. So there is a need to balance all of those things together. Now, once you've got an idea of exactly how much solar or what kind of wind you want to put up, this is where we can actually do some estimates of power production. So the things that you need to know is which system you're going to use. What is the generation capacity? So a wind turbine like the one here, that's called a SkyStream, it generates about 2.4 kilowatts or 2,400 watts. These solar panels here, they might, run 250 watts a piece. You need to know how many of those you're gonna have. And that way we can actually start doing some power production estimates. So the system size, when it comes to wind turbines, not necessarily solar, you need to know things like how tall the tower is and how long the blades are or how large the rotor diameter is. With solar, you need to know how big the solar panel is so you can better understand how many of them you can fit on your rooftop or something like that. And then for some, it's easy to just look at the power curve instead of making these estimates and calculating them through various equations. But first we will go over the theoretical equation. So this is what we call the power equation. It will calculate the power in watts that is in the wind. So this is the amount of power that's available in the wind that is available at your site. We will talk more about how much you can actually capture with a wind turbine in the next slide. So here, power in watts is equal to 1/2 times the air density times the swept area. So again, knowing your rotor diameter, you should be able to identify your swept area. And then you need to know your wind velocity. And that is, again, from the last task, understanding your resource assessment, how much wind is available at your site. And again, making sure that that's the wind that's available at however high your turbine is going to be. So assuming we have all that information and we can calculate a power in the wind, now we have to understand how much a wind turbine can actually capture. So a wind turbine captures the kinetic energy in wind by converting it to mechanical energy via a spinning rotor, and then to usable electrical energy by way of a generator or an alternator. The thing is that there is something called the Betz limit, and this is the theoretical maximum amount of kinetic energy that can be captured by a wind turbine, and it's roughly 60%. And again, that's a maximum. So we can assume that their maximum efficiency, the blades, but that's not always going to be true. And then we can make an assumption in terms of the actual efficiency. So overall, these small wind turbines can expect to produce electrical energy with about 20 to 40% efficiency, from the energy that we captured with the blades to the energy that eventually gets created into electricity. There's losses, so 20 to 30% efficiency. So once we apply all those efficiencies, then we might be able to get an accurate reading of how many watts you could actually get from that wind turbine in that wind regime. The other thing we can do is we can look at the power curve of the turbine that we're looking to install. So this is a generic power curve, but if you search online, you can find power curves for any wind turbine that you're looking at. And so what you do is you are looking at this graph, and it's telling you about how much power in kilowatts or watts you can expect out of that turbine at different wind speeds. So you can see at about 3.5 meters per second, this turbine starts to generate electricity. That's what we call the cut-in speed. And then at the very other end of the graph, you can see at 25 meters per second, that turbine stops generating electricity, and that's what we call the cut-out speed. That's at the point where the generator could be damaged if it's operating at such a high wind speed. And then in the middle, we have what we call the rated output speed. And so if you were looking at a turbine that generates 2.4 kilowatts, that is the speed at which you reach 2.4 kilowatts and can sustain that. And here it's 14 meters per second. And then everywhere between 3.5 and 14 meters per second, you're seeing an increase in the power over the wind speeds. And so you want to make sure that your annual average wind speed falls somewhere probably in the upper end of that power curve. That will tell you about what you might see in terms of power during the year. So assuming you've used the power equation or the power curve to understand how much power this turbine can produce at the wind speeds that you have at your location, it's important to understand that power is different than energy. And energy is what we consume. So when you look at your electric bill and when you did your energy assessments, you're looking at kilowatt hours. And power is energy consumed per unit of time, so power is a reference to the potential instantaneous output of a device, and then energy is reference to the output of a device over a period of time. So power times the time that it's operated or used equals the amount of energy consumed or generated. So if we had 1,000 kilowatt turbine, or a thousand kilowatt turbine that we used in 1 hour, we'd use 1,000 kilowatt hours, or we'd generate. And so this is hopefully something that's a review from that earlier task. The other thing to consider, which I know we talked a little bit about in the siting part, but we also want to reiterate here, is that you have to make sure, again, that you're putting your turbine far enough away from things so that you're not influencing them with sound, flicker, visibility, reducing property values, or impacting wildlife. And again, proper siting will eliminate all of these issues. So I know we didn't get a lot into the solar side, but there's a website that's called PV Watts that we will get into later, that you actually just input all that information in and it'll spit you out production estimates. So that's why I didn't get too far into that. So with the methodology, again, we're going to be researching our wind and solar technologies, selecting a couple of different types to further investigate. You may pick a couple of turbines and a couple of different solar panels because you don't know exactly which one's going to perform the best. Review all the specifications for your systems, and then using your solar and your wind measurements from the last task, calculate your total power and energy produced from the systems. If you use a frequency distribution of the winds over the power curve, you can also get the same information. We want you to come up with 3 scenarios for generating power with renewables. And this is a suggestion, just one with just wind, one with just solar, and then one with a combination. But maybe, you want one with 2 turbines, one with 1 turbine, and one with solar. I don't know. You can decide on your scenarios and then also create a budget for these scenarios. And that way you can look at them side by side and discuss the potential community impacts for each, and then select the best scenario. And again, we want you to discuss the limitations of your siting and resource assessment and reflect on your procedure. Again, the tools, like I said, we'll use Excel. Windographer is another program that you can use for your resource assessments, and then also will allow you to do some power production estimates. In terms of internet sources, PV Watts, again, is a great location for you to do some solar estimates, and Solar PV Guide will also help you with solar estimates. And then the SkyStream specifications are right here, so if you want to use the SkyStream as your turbine of choice, you can get those specifications right here. And then helpful activities. The Center for Wind Energy has created a resource assessment lesson plan. We're more than happy to provide that to anyone who's interested in it. It uses Excel and walks through the entire process that we just explained throughout resource assessment and production estimates. The WindWise education curriculum, which is free at KidWind, has a unit specifically on wind and measuring wind, so that's a great unit to use in your class. And the Need Wind for Schools curriculum has some calculating wind power and submitting an estimate activities that could be helpful in your classroom. Again, a suggested rubric, understanding that we're doing power production estimates for a couple of different scenarios, budgets for a couple of different scenarios, and then discussing the limitations and recommendations. The timeline for this, again, the time of the year is however you want to take that. We were planning this as an April 1st start date, ending in the first week of June, which gives us 9 weeks to complete this part of the task. It is pretty lengthy with the power production estimates and then the budget. So 9 weeks hopefully is appropriate. So if you need any help, again, please contact me anytime at the Center for Wind Energy. Or again, we always suggest that you contact a local solar or wind installer for your help, because they are usually very excited to work in the schools and get students engaged in their industry. Good luck.